Okay, good morning, everyone. This is Haeun Chung. I'm an assistant research professor at Far Observatory, working on various UV missions here over the last 5 years. And today I'm happy to talk about the mission that I'm PIing, the mission called NOX for the Earth Sky Far UV background mapping. Okay, so as an astronomer, my primary interests are in the circumgalactic medium and the intergalactic medium around the cosmic web and the galaxies. And in particular, where the Decadal Astro 2020 Decadal survey recommends, and as one of the discovering area, doing the mapping of CGM and IGM in emission. So here, the left figure shows the materials around the galaxy halos, which are the building blocks and the fuel for the star formation and the evolution of galaxies. And it is showing its distribution in 2D in various spatial scales. And we would like to observe these in emissions so that we can actually see this. This is simulated images, but we would like to actually see this kind of distribution from the sky. So that's why the Decadal recommends this. Yeah. One of the challenge is that these CGM emissions, these are not stars, these are gas making emission lines, and they're very faint. And most of the useful emission lines are in far UV, which you need to go into the space to observe them. And like for example, the 10 line unit that I put here, this is like extremely faint. We are doing Aspera, which is observing this emission line in around 1,000 line unit, and this is already like 100 times fainter than that. And another challenge on top of that faint emission line is about the background. So when you're trying to observe this kind of faint features, then you must know about the background, otherwise you cannot actually plan anything. So okay. Oh, yeah. So here on the left image, plus shows the like how much exposure time you need to observe certain like line emissions at given like background level. And if you focus on the top solid line, then you will see that if the background is like only 10 continuum unit, then you need like 31 hours of exposure time to observe such emission. But if background is like 100 times brighter, then you need significantly more time to observe such. And these are like simulation with 6-meter class future flagship missions. So the main point here is that if you do not know about the background, then you cannot actually plan for such observation with the future mission. Then let's see like how much knowledge you have for this Far UV background as of year 2024. So here this plot shows the complete cosmic background spectrum. The x-axis is the frequency of the light and y-axis is the flux. And you will immediately notice there is a like gap in the middle, which is far UV wavelength range. And that's because like we didn't have much, this UV wavelength range is kind of underexplored area. So we didn't have much previous missions to actually characterize the background level at that wavelength range. We do know some information from only like 2 missions. So at Far-UV, at wavelengths between 130 to 175, we essentially have actually only single data point with spectral resolution of 3 because they are from imaging data, which are from the Galaxy mission and the Sphere mission. So those covered are about the same wavelength range, but again, to estimate the continuum, its spectral resolution is very low. And if we go more shorter wavelengths, like Lyman UV from 90 to 150 nanometer, there is only one mission who planned to measure such continuum at that wavelength, which is Sphere. But when they were in orbit 20 years ago, they got like 20 times less effective area than their original plan. So it was not sufficient to do such observation. So to fill that missing knowledge gap, this is the mission concept that I have called NOX. So this is the mission concept to do the Earth Sky Far UV background mapping. with the step and stair concept observation. It's the imaging spectrograph, and I believe that with NOx, this mission is going to provide the foundation and baseline for our future UV missions. Well, I'm the PI, and here are the team members that we are working together. Like there are some local industry members and JPR, Goddard, and other collaborators. Where the goal of NOx is one of the decadal goal, the unveiling the drivers of galaxy growth. And we have like two specific science objectives. One is like determine the intensity and the distribution of this far-UV background. And also second one is to determine the spatial distribution of Milky Way, our local the Milky Way, the warm hot halos around our local Milky Way, which is actually kind of byproduct of this NOx. This is a small satellite mission, so to provide like knowledge and heritage for the future mission. This another objective of NOx is serve as a test bed for the state of art far-UV technologies, the UV coatings, gratings, and detectors. And this is the current like schematic payload design with the optical path. There are like multiple reflections, which may freak out some UV people over here. But this is very small, 3 centimeter diameter the telescope and the spectrograph. The telescope is a 3-meter anestigma telescope, which provides wide field of view with good imaging quality, 2.5 degree by 1 arc minute. And the wavelength coverage is actually pretty much same as the previous mission called Film Sphere, but this one would provide better sensitivity. And we have like the silicon grading for the future, the UV grading technology, and we plan to use EMCCD as a detector. And here is the big part, which is sensitivity, where as per my sensitivity calculations, we expect to achieve like 2009 unit, which is of oxygen emission line detection, which is 10 times deeper than previous mission at this spatial scale. And for the continuum, which is the background, we expect to reach like unprecedented or like low surface brightness level, which is 20 continuum unit. And if we got selected in some future funding opportunities, then we will build all this at UA, at the payload, and those will be based on the heritage and lessons learned from the current mission that we are doing at UA, current UV missions that we are doing at UA, the Aspera, Fireball, Simcoe, and etc. So here is the brief history and the path forward with NOx. So this is not the first mission. Actually, we proposed this to NASA APRA program back in December 2021, and we got declined. But as a 12U CubeSat mission, but we didn't get funding, but we got like great comments. That's of course always the information to move forward. And also like just a few months ago, we proposed another like technology development proposal to the same program, which is testing this UV grading with the UV coating, which is gonna be like directly applicable for the mission like NOx. And this is under review right now. I think literally this week is this review happening. And if this thing gets funded, then I think it's gonna be the great motivation to move forward with NOx. And thinking out future, so regardless of the current proposal that we put, we will actually propose this mission as a SmallSat scale to the next coming astrophysics pioneers mission class, same as Astra class, 20 million, and see how things goes. And I propose them all as PI over here, and for the previous two mission proposals, like technology proposals, I got a great support from UASI for the proposal preparation. So I highly appreciate those supports. And here's summary where this far-UV background is needed, and someone has to do this with this specialized telescope. So we would like to propose this into the future opportunities and to run this mission. And I will take questions.